So in section 5.2, okay, talking about logarithmic functions, and I sent you an email with a link to a short video that I made on where logarithms come from. Okay. So let's just review that real briefly. So in section 5.1, we studied exponential functions. And so, you know, the graph of an exponential function looks something like that. So let's write out the function, right? So an exponential function is of the form f of x equals a to the x, where a is greater than 0, not equal to 1. Okay? So in my graph over here, okay, a is greater than 1. Right? If a is greater than 1, then the graph of the exponential function goes up, right, from left to right, and it crosses the y-axis at 0.01, right? 0.01, the y-axis is the y-intercept. Okay. Well, the graph of this exponential function, the exponential function passes the horizontal line test. If it passes the horizontal line test, it has an inverse function. What's its inverse function? Well, given some points on the graph of the exponential function, okay, we can plot the corresponding points of the inverse function by just switching the x and the y coordinates. Right? Recall from when we were in our discussion, the section on inverse functions. So the inverse function, or the exponential function, right, instead of going through the 0.01, it goes through the 0.10. And the graph of an inverse function, of a 1-1 function, okay, is reflected across the slanted line y equals x. Now we discussed all this on the section on inverse functions. Okay, and so the graph of the inverse function for this exponential function looks something like that. Okay, I'm drawing it by hand, so it's not perfect. Okay, but this graph, right, the graph of the inverse function, right, is a reflection of the graph of the exponential function across that diagonal line, y equals x. This inverse function, okay, is called a logarithmic function. It's an exponential function. And the notation for this inverse function is log base a of x. Okay. This notation for a logarithmic function, and this logarithmic function is the inverse function of a to the x. Log base a of x. Another way of seeing why we have this notation, given this 1-to-1 function, f of x equals a to the x, you know, to find its inverse, we replace f of x with y, and then we switch x and y. We have x is equal a to the y power. We cannot solve for y algebraically. Okay. So mathematicians way back when had to come up with a name, right, of a function that equates x to a to the y power. And what they came up with was log base a of x. Okay. And so the logarithmic function is just the inverse of the exponential function. Okay. And you know, so y equals log base a of x, right? This is just a fancy way of expressing this exponent y that equates a to the y to x. Okay. And that's sort of a synopsis of my little video. Okay. So what I put on the board basically deals with this first sentence at the top of your notes, okay? And if we have this logarithmic function, y equals log base a of x, okay, then that is equivalent to this equation up here, x equals a to the y. So if we have a logarithmic equation like this, we can rewrite it as an exponential equation. And if we have an exponential equation like this, we can rewrite it as a logarithmic equation. Okay? They're equivalent equations. Okay? We have properties of logarithms, just like we have properties of exponentials, okay, which we reviewed yesterday. And these are the four properties. And the two that are the easiest to remember is the log of 1, the number 1 in any base is equal to 0. Okay? And the reason for that is if I convert that from logarithmic form to exponential form, I have a to the 0 is equal to 1. And that's a true statement. Okay? So a to the 0 equal to 1 and log base a of 1 equals 0 are equivalent statements. Okay. In the second one, we have log base a of a is equal to 1. And so the equivalent exponential statement is a to the first power is equal to a. And that's a true statement. Okay. And properties 3 and 4, okay, also follow from this relationship here. Log base a of a to the x is just equal to x, and a raised to the log base a of x is just equal to x. And that's because the logarithmic function and the exponential function are inverse functions of each other, so they undo each other. And so everything cancels out, and you're just left with the x. All right, so let's put some of this, what we know about logarithms, to use. So in the first exercise, right, you're given 3 logarithms, or you're given 3 expressions, okay, and we got to evaluate the value of each expression without using the calculator. So in A, we have log base 2 of 16. Okay. Now there are other ways to solve this, but we're going to solve this using the properties of logarithms. Okay. What's that equal to? Okay. So what we're asking is, remember, this logarithm is equal to some value of y that equates a to the y to x. So one way of looking at this is equal to y, so converting to exponential form, 2 raised to the y power is equal to 16. The question is, what value of y, 2 raised to what value of y is equal to 16? But we're going to use properties of logarithms to demonstrate them. And 16, you know, can be written as 2 to the 4th power. Right? 2 to the 4th power is equal to 16. Actually, I guess I got to go down based on the space provided under notes. And so this looks a lot like property 3, where a is equal to 2 and x is equal to 4. Right? Property 2, or property, excuse me, 3. So according to property 3, this is just equal to 4. Okay. And what I had written on the board, 2 to the y is equal to 16. Y is equal to 4. All right, in B, we have log base 10 of 0.01 is equal to what? Okay. Well, 10 to the minus 2 is the same as 1 over 10 squared. 10 squared is 100, and 1/100 is equal to 0.01. Okay. So we can replace 0.01 with 10 to the minus 2 power. And so then again, by property 3, this log base 10 of 0.01 is just equal to minus 2. Again, in solving this logarithm, you could have asked yourself, 10 raised to what power is equal to 0.01? And the answer is y is equal to minus 2. Right? 10 to the minus 2 is equal to 0.01. And then lastly, in C, we have 3 raised to the log base 3 of 7. That looks a lot like property 4, with a equal to 3 and x equal to 7. And so this is just equal to 7. Okay. All right, any questions on that? So logarithmic functions and exponential functions are inverse functions of each other. Okay. Logarithmic functions are just a fancy way of writing an exponent, writing the value of an exponent. Okay. In exercise 2, we got to change each exponential statement to an equivalent logarithmic statement. So remember, if x, from the top of your page, if x is equal to a to the y, right, then y is equal to log base a of x. Okay. So this is an exponential. A is the base, right? We did this yesterday. Y is the exponent. And then x is the value of the exponential. So in the logarithmic statement, a, right, the base of the logarithmic statement is the same as the base in the exponential. Okay. Remember, this a is a subscript on the word log. Okay. So don't put it straight across, it's a subscript. So it's log base a of x. Okay. And y, right, is the exponent in our exponential. Okay. So we're saying that exponent y is equal to log base a of x. Okay. So logarithms, right, are just a fancy way of expressing an exponent in an exponential. Yes, sir?
What does it say about the x value of the exponent?
Exponential. Yeah. So in exercise 2, you're given 8 is equal to 2 cubed, right? That's a true statement, right? So the base a in this case is 2, the exponent y is 3, and the value of the exponential is 8. So it's true, right? So going from this form to this form, we have y is equal to log base 2 of 8. In B, we have 3 to the x is equal to 4.6. Now this is one where you got to pay attention, because x is not over here. X replaces y in the x as the exponent, right? So now we're moving variables around. So the role of x is changed in this one. X is now in the place of y as the exponent. Okay. So 3 is the base. X is the exponent in our exponential. And 4.6 is the value of the exponential. So this exponent x is equal to log base 3, right? The base is 3 of 4.6, the value of the exponential. So you got to be careful when they move variables around, change their role. Okay? Yes, sir.
For example A, why wouldn't you change the y to 3?
And you know what? You're absolutely correct. Okay? Y is equal to 3, right? And so, yeah, so it should be 3 equals log base 2 of 8. Okay? I'm going from my equation over here to over there.
I didn't know.
I brought the y. No, I'm glad you brought that up, right? That's a very good question. Okay. Why isn't the y at 3? It is 3. Y equals 3. Okay. So yeah, so it should be 3 is equal log base 2 of 8. Okay. So if 8 equals 2 cubed is a true statement, then it has to be a true statement that 3 equals log base 2 of 8. Okay. If this is true, then this has to be true. If this is true, then this has to be true. And over here, if this exponential is true, then this logarithmic statement has to be true. And if this logarithmic statement is true, then this exponential statement has to be true. If one is true, they're both true. If one is false, they're both false. All right. So thank you for asking that question. Okay. All right. In exercise 3, okay, we're going to do the reverse. You're given a logarithmic statement, and you got to write the equivalent exponential statement. Okay. So again, okay, given an exponential, if the exponential statement is true, then the logarithmic statement has to be true. And if the logarithmic statement is true, then the exponential statement has to be true. Okay. So in A, we have log base 4 of 164 is equal to minus 3. Now usually when you look at an exponential statement, you know right away whether it's true or false. But when you look at a logarithmic statement, that's not so obvious. And so, but by converting it to the equivalent exponential statement, you know whether the logarithmic statement is true or false. Okay. So 4 is the base, minus 3 is the exponent. Okay. And 1/64 is the value of the exponential. Okay. So the base A in this case is 4. Y, the exponent, is minus 3. And x, right, is equal to 164. So substitute for x, a, and y. In our exponential, we have 164 is equal to a, which is 4, raised to the y power, minus 3. Now you can reverse, right, the two sides and write as 4 to the minus 3 is equal to 164. You can switch the two sides. Is that a true statement? Is 4 to the minus third power equal to 164? Yeah. Because 4 to the minus 3 is equal to 1 over 4 cubed, and 4 cubed is equal to 64. So this is a true statement up here. Right? So the equivalent exponential statement to this logarithmic statement, okay, is 1/64 equals 4 to the minus 3 power, or 4 minus 3 power is equal to 1/64. All right, in B, we have log base 3 of 9 is equal to 2. So 3 is the base of the exponential, or the logarithmic statement, and 2 is the exponent. So A is equal to 3, Y is equal to 2, and X is equal to 9. So A to the Y, right, is equal to X. A in this case is 2, or excuse me, A in this case is 3, Y is 2, X is 9, and so we have 3 squared is equal to 9. Is that a true statement? So then it's true that log base 3 of 9 is equal to 2. Okay. So logarithms, again, are just a fancy way of expressing this exponent using the base of the exponential and the value of the exponential. Okay. Any questions on that? Okay. So if you flip over your handout, we're going to look at some graphs. I used to put all this, last semester, put all this stuff on the board. Everybody had to copy it down like crazy. I thought this semester it would be better if I just put it on the handout and then we can just walk through it together. All right. So in exercise 4, right, it says on the same coordinate plane, sketch the graph of the following functions. F of x equals 2 to the x, and g of x equals log base 2 of x. Now, I unwittingly graphed these very functions in my video, if you watched my video, okay, on the development of logarithmic functions. And so graphing f of x equals 2 to the x, right, is a throwback to yesterday's lecture, right, because we were graphing these things. And so this is a graph of f of x equals 2 to the x, right? It goes up and to the right, right, from left to right, crosses the y-axis at y equals 1. Now, the inverse function, okay, for f of x equals 2 to the x can be found by reflecting the graph of 2 to the x across the diagonal line y equals x, and the graph of g of x equals log base 2 of x, right, by taking points on the graph of 2 to the x and switching the x and y coordinates, we get the graph of g of x, which is log base 2 of x, okay, which is basically what I did. So, in general, when the base is greater than 1, the graph of the exponential function goes up and to the right, crossing at y equals 1, and the graph of the logarithmic function, right, also goes up and to the right, crossing at x equals 1, right, on the x-axis. X equals 1 is the x-intercept. Okay. And so these two graphs are reflections of each other across the diagonal line y equals x. Okay. So this log base 2 of x is the inverse of 2 to the x, and 2 to the x is the inverse of log base 2 of x, right? They're the inverse of each other. Okay. So in general, if the base of the logarithmic function, okay, a is greater than 1, then it'll look like, it'd be similar to the graph of log base 2 of x. Okay. They will all cross, right, log base a of x, if a is greater than 1, will cross the x-axis at x equals 1, right, going up and to the right, from left to right. Okay. The domain, if you look closely, the domain, oh, one thing, remember with inverse functions, the domain of the logarithmic function is equal to the range of the one-to-one function, okay, of the exponential function. And we know the range of f of x is from 0 to infinity. So you can see down here, right, the domain of the logarithmic function, right, is from 0 to infinity. The vertical line x equals 0, which coincides with the y-axis, is a vertical asymptote. That's what we have down here. That's what VA stands for, vertical asymptote. So the vertical line x equals 0 is a vertical asymptote. And where the graph crosses the x-axis is at 0.10. That's the x-intercept. And then the range, you can see there's no minimum y-coordinate and there's no maximum y-coordinate. So the range goes from minus infinity to plus infinity, which is the same set of numbers, right, for the domain of the exponential function. Okay. Because they're inverse functions of each other. Okay. If the base of the logarithm a is between 0 and 1, right, then the graph goes down from left to right, crossing the x-axis at x equals 1. But it has the same domain, range, intercept, and vertical asymptote as in the case when the base is greater than 1. Okay. Now, you'll notice, right, with the domain, x has to be greater than 0, right? So you cannot take the log, you should know, you can't take the log of 0 or a negative number because x less than or equal to 0 is not in the domain of the logarithmic function. Okay? Are you with me? Okay. So you can't take the log of 0 or a negative number. Okay. So in exercise 5, right, we're instructed to graph the following function and state the domain, range, and asymptote. Okay. So you'll notice, right, this is not log base 4 of x. This is the transformation of the function log base 4 of x. Okay. So let's see how I came up with that graph. Okay. Then we'll talk about the domain, range, and vertical asymptote. So if we start off with the equation log base 4 of x, we know from up above the graph of that equation looks like that, right? Crosses the x-axis at x equals 1. And then if I replace x with x plus 3, when you replace x with x plus 3, what does it do to this graph? Shifts it which way? To the left 3, right? So it shifts the graph to the left 3. Now, I mean, this is all goes back to transformation functions, okay? Math is not something that you study this topic today and then you forget about it, right? You take it all with you to the next topic, okay? And then to finish, the next transformation is we multiply the right-hand side, or we take the negative of the right-hand side. Right? When we put a minus sign in front of log, we're multiplying by -1. And when you multiply the right-hand side by -1, what does it do to the graph? Then, you remember? Transformations.
Does it scale it negative?
You're like,
Flips.
Well, it flips. How does it flip it?
X-axis.
Across the x-axis, right? So it reflects the graph across the x-axis. So to go from this graph to the graph of minus log base 4 of x plus 3, I take this graph and shift it to the left 3 units, and then flip it over the x-axis. And when I do that, I end up with this graph right here. Okay. Now, without the graph, in finding the domain of a logarithmic function, this inside the parentheses here, we call this the argument. Okay? And so, the argument in our logarithmic equation is equal to x plus 3. And so to find the domain, remember you can't take the log of 0 or a negative number. And so you set the argument to greater than 0. Right? Up above, the domain is x greater than 0. So instead of x being greater than 0 for the domain, we have x plus 3 is greater than 0. That's an inequality. So when you solve for the inequality, you get x is greater than -3, right? In the interval notation, that's -3 to infinity. Okay. The range, tell by just visual inspection, okay, goes from minus infinity to minus infinity to plus infinity. Okay. And the vertical asymptote, right, up here the vertical asymptote was x equals 0, right? Basically by setting the argument up here x equal to 0. So down here, the argument is x plus 3, and so you just set the argument x plus 3 equals 0 and solve for x, and you get the vertical line. Remember, vertical asymptotes are vertical line, so the vertical line, x equals -3 is the vertical asymptote. Okay. So instead of the vertical line x equals 0 being the vertical asymptote, right, it's x equals -3. Okay. Now all this stuff, right, you can get it algebraically, right, the domain and the vertical asymptote, right, and the range should always be minus infinity to infinity. Okay. So you can get this information algebraically or by drawing the graph, right, by performing the transformations. Okay. Any questions on that? All right, so flip over your handout. You know, yesterday we talked about the number e, right, where it came from, okay, how it's sort of an amazing number, right, because it's the limit of a sequence, okay, the result of a sequence of numbers. So if we can have an exponential function, right, with a base of e, we're going to have a logarithmic function with a base of e, right? Because remember, the logarithmic function is the inverse of the exponential function. Okay. So now we have what's right. We learned about the natural exponential function yesterday. So now we have a new function, right? The corresponding logarithmic function to the natural exponential function. is called the natural logarithmic function. Okay. And the natural logarithmic function has a base of e. Right, so we're replacing the a with e. Okay. So if we have y is equal log base a of x, and we replace a with e, the number e, then we have y is equal log base e of x. Okay. Now, because the number e is such a special number, the natural logarithmic function gets its own special notation. Okay. So this is pronounced ln of x, so we replace log base e with ln. And so the natural logarithmic function gets its own special notation. Replace log base e with ln. Okay. Now let me make a comment. About this function. This is not ln times x. Let me write this. This is pronounced ln of x, but you will also hear me say quite frequently pronounce it as the natural log of x. Okay. And let me say something about this notation. Okay. Right, you know function notation. So if I write f of x, right, you know f is the name of the function. And x is the input to the function. Okay. So you should think of ln as a special name of the function. Okay. So we could write ln of x, right? Put the x in parentheses, just like we do with f of x. Okay. And so ln is a special name of a special function. And x, right, is still the input to that special function. But because this is a special function with a special name, we often drop the parentheses and just write ln of x that way. Okay? So when you see this, you should think of this like you think of f of x. Okay? This is not multiplication. I mean, I see people all the time solving a problem. They'll do like 2x plus 5 divided by ln, and that makes absolutely no sense whatsoever. Right? That's like writing 2x plus 5 divided by square root. That makes absolutely no sense. Okay? So, ln, right, has to have an argument. Remember, what goes into the logarithm, we call the argument. Okay? And so ln has to have an argument as well. Okay? You just can't write ln all by itself. It makes absolutely no sense. Just like writing square root by itself. It makes absolutely no sense. Okay? All right. So there are properties of the natural log function, okay? And they follow directly from the properties of logarithms with base a from page 1. So what you see on page 3 for the natural log is the same as these, but you replace log base a with log base e, and then you replace log base e with ln. And you end up with these 4 properties on page 3. So the natural log of 1 is equal to 0. And on page 1 we said that the log of 1 in any base is equal to 0. The natural log of the number e is equal to 1 because the natural log function and the natural exponential function are inverse functions of each other. the natural log of e to the x is equal to x, right? This exponent x. Again, because the natural log function and the natural exponential function are inverse functions of each other. And finally, for e raised to the natural log of x is just equal to x, because again, they're just inverse functions of each other. And so in exercise 6, right, we're instructed to graph the natural exponential function and the natural log function. Again, we did this yesterday, graphing the natural exponential function. So this is in your 5.1 notes. And you know, like any exponential function with a base greater than 1, the graph goes up and to the right, crossing the y-axis, that y equals 1. And then the graph of its inverse, the natural log function, is similar to the graph of the inverse of any exponential function, right? This is a graph of the natural log base e of x, which is ln of x, crosses the x-axis at x equals 1, and it's a reflection of the graph of the natural exponential function across the diagonal line, y equals x. Okay. Any questions on that? So we'll stop right there. And tomorrow we'll review the arithmetic properties of, right, just as there are arithmetic properties of exponentials, there are arithmetic properties of logarithms. We'll go over those and work the exercises at home. Okay? So have a good day. I'll see you tomorrow.